I am Dr. Mamta Bhusry from Department of Computer Science and Engineering, Ajay Kumar Garg Engineering College, Ghaziabad. This is my second lecture on distributed databases, and here we will start from distributed transactions. A transaction, as we have already seen in the previous lecture, may access data at several sites. Each site maintains a transaction manager which is responsible for participating in coordinating the concurrent execution of the transactions executing at that site. When we talk of concurrency control in databases, then the concurrency control techniques, they are the same as centralized databases, but extended to distributed databases. We will concentrate on the locking techniques over here. Various approaches to 2PL, that is the two-phase locking, exist. These are based on the two-phase locking protocol of the centralized databases. The only difference is in how the lock manager deals with the replicated data. The first approach that we will do is the single lock manager approach. In this case, the system maintains a single lock manager that resides at a single site, say SI, and all the lock and the unlock requests, they are made at SI irrespective where the data is stored. When the transaction from any of the sites needs to lock a data item, it sends a lock request to the site SI, and the lock manager determines whether the lock can be granted immediately or not. If the lock can be granted, then the lock manager sends a message to the site which initiated the lock. If the lock cannot be granted, then the request is delayed until the lock can be granted, at which time the message is sent to the initiating site. The transaction can read the data from any of the sites where the data is replicated. The data item is locked in a shared mode at only this site. Writes was performed on all the replicas of the data item, and the data item is locked in the exclusive mode at all the sites where it exists. The advantages of this technique are simple implementation and simple deadlock handling, because all the lock and the unlock requests, they are made at a single site. The disadvantage is a bottleneck that can be caused at the site where the lock and the unlock requests are sent, because all the sites, they are sending the request to this site. And secondly, failure of the lock manager site may result into no lock requests from any other sites, and hence a loss of concurrency control. The second approach is the distributed lock manager approach. Here the lock manager function is distributed over several sites. Each site maintains a local lock manager. The lock manager at each site determines the lock and the unlock requests for the data items that are stored at that site. To access a data item not present at the site, request is issued to lock the data item where the data item is stored. If the lock can be granted, then the message is sent. If the lock cannot be granted, then the request has to wait. The advantages of this approach are that it reduces the bottleneck, as in the previous case where the lock and the unlock requests are made at a single site. Disadvantages are that the deadlock is complicated. There may be a deadlock even if there is no deadlock at a single site. Now, let us say we have T1 is a transaction at site S1 and T2 is a transaction at site S2, and the transaction T1 at site S1 is waiting for a data item which is held by the transaction T2 at site S2 in an incompatible mode, and the transaction at site S2 is waiting for a data item Y which is held by the transaction T1 at site S1. So, in this case, even though X and Y are at different sites, T1 and T2 are being initiated at different sites, but a deadlock exists because T1 is waiting for the data item at site S2 and T2 is waiting for the data item at site S1. Several variants of the lock manager approach are there, which are primary copy, majority protocol, bias protocol, and the quorum consensus. Primary copy means that one replica of the data item is chosen as the primary site, is chosen as the primary data item. The site containing the replica is called the primary site or the primary site of the data item. Different data items can have different primary sites. When a transaction needs to lock a data item Q, it requests a lock at the primary site of Q. If the lock is granted, then the data item Q implicitly gets locked on all the replicas where it is existing. Advantages: simple implementation. The concurrency control for replicated data is handled in a manner similar to unreplicated data. But the disadvantage is that if the primary site Q fails, then Q is inaccessible even though other sites containing the replica of Q, they are accessible. The next technique is the majority protocol. Here, local lock manager at each site administers the lock and the unlock requests for the data items which are stored on that site. In case of replicated data, when a transaction wishes to lock the unreplicated data item Q residing at site S I, a message is sent to S I's lock manager. If Q is locked in the incompatible mode, then the request is delayed until the lock can be granted. When the lock request can be granted, then the lock manager sends a message back to the initiator indicating that the lock request has been granted. Now, what happens in the case of replicated data? If Q is replicated at n sites, then the lock request message must be sent to more than half or more than 50% of the n sites at which Q is residing. The transaction does not operate on Q until it has obtained a lock on the majority of the replicas of Q. When writing the data item, the transaction performs the write on all the replicas. Advantages: it can be used even when some of the sites are unavailable. However, some mechanism has to be devised to handle the writes in the presence of the site failures. The disadvantages of the technique are that it requires more messages for handling the lock and the unlock requests. Also, there is a potential for deadlock even with a single data item. Let us consider a data item Q which is replicated at 4 sites S1, S2, S3 and S4 with full replication. Now, say the transactions T1 and T2 both wish to access the data item in the exclusive or X mode. Say T1 succeeds in locking Q on the sites S1 and S2. So, T1 succeeds in locking Q in the exclusive mode on the sites S1 and S2, and the T2 succeeds in locking Q on the sites S3 and S4 in the exclusive mode. So, T2 locks the data item on S3 and S4. Now, each transaction, it has to wait to acquire the third lock to be able to complete more than the 50%. But since lock is acquired by T1 on 2 sites, lock is acquired by T2 on 2 sites. So, both T1 and T2, they have to wait for each other to release the lock so that they can acquire it. This leads to a deadlock situation. The next is the bias protocol. In the bias protocol also, the lock manager at each site exists as in the majority protocol. However, the requests for the shared and the exclusive locks, they are handled differently. Shared locks, when a transaction needs to lock a data item Q, it simply requests a lock on Q from the lock manager at one site containing a copy of Q. Whereas for the exclusive lock, when the transaction needs to lock the data item Q, it requests a lock on Q from the lock manager at all the sites where the replica of Q is there. This method is more significant when the transactions are read-only transactions, because in the update transactions the amount of overhead on for the updates will be very large. So, the advantage is that it imposes less overhead on the read operations, and the disadvantage is that there is a lot of overhead on the write operations. The next topic that we will take up is deadlock handling in distributed databases. Now, consider two transactions with the item X and transaction T1 at site 1 and item Y and transaction T2 as site 2. So, we have two sites at T1, we have the item X, at T2 we have the item at site 1 we have the item X, at site 2 we have the item Y. T1 is executing here, T2 is executing here. So, let us see how it happens. We have a X lock on the data item X, write X, X lock here on data item Y, write Y. Now, this is waiting for X lock on X. So, the transaction T2 at site 2 requires a X lock on the data item X, and the transaction T1 at site 1 requires a X lock on the data item Y. So, what has happened is this will result in a deadlock. Why? Because none of the transactions can proceed. Now, if we consider, we already know that we have the deadlock prevention and the deadlock detection techniques for deadlock handling in centralized databases. Considering the deadlock prevention technique in the distributed databases, the same algorithm as in the central database, they can be applied, but there will be unnecessary waits and rollbacks as more sites are involved in the distributed systems. Hence, this is not a preferred method. The preferred method is of deadlock detection and removing the deadlock. Each site in the distributed system maintains its own local wait for graph. The nodes of the graph correspond to the transactions, local as well as the global, that are currently holding the data item or requesting the data item at that site. We know that the wait for graph is the method for deadlock detection in the centralized databases. So, let us say at site 1 we have the transactions T1, T2, T3 and T5. At site 2 we have the transactions T2, T3 and T4, and both the sites they are maintaining a wait for graph. Now, for the global transactions in data items, when a transaction Ti on the site S1 needs the data item on site 2, it sends a request message to site 2. If the data item is held by another transaction Tj, then the system inserts the edge Ti to Tj in the local wait for graph of site 2. If any local wait for graph has a cycle, then a deadlock occurs. But no cycle in the local wait for graph does not mean that there can be no deadlock. The local wait for graph for the sites 1 and 2, they are cyclic, they are acyclic, that we have already seen here. So, there is no deadlock at the site 1 or at site 2. But here what we have done is that we have made a union of the two local wait for graphs at site 1 and 2. The moment we do this, we see that there is a cyclic path over here, which indicates a deadlock. For the deadlock detection in distributed databases, a centralized deadlock detection approach is used. The system maintains a global wait for graph at a single site, which is called the deadlock detection coordinator site. The global wait for graph is updated under the following conditions: whenever a new edge is inserted or removed from one of the local wait for graphs, or periodically. Whenever the coordinator needs to invoke the cycle detection algorithm, then when the coordinator invokes the algorithm, it searches the global wait for graph. The coordinator notifies all the sites that a particular transaction has been selected as a victim if there is a deadlock, and the sites roll back the victim transaction to remove the deadlock. Thank you.